Before we took the lunch break, we were discussing about how to derive the noise factor for a inductor degenerated amplifier. Now in that, we found out or we used the definition of noise factor F, and we said that we know output noise due to transistor noise that is known to us, and then we need to determine the output noise due to source resistance. So let us do that. Find out the output noise due to source resistance. Look at the circuit. Remember the circuit that we have, or the equivalent circuit for the transistor. On the left side of the dashed line is the source, which means RS, noise, and the inductor LG. So from that side, if you look to the device, the impedance is ZD. Device impedance, input impedance at the device is ZGS. Across the gate source or junction, the impedance is ZGS, and the capacitance is CGS. Voltage across that capacitance is VGS. Then the current through the device is controlled by VGS. The current is GM into VGS. There is a noise. The noise current is I NDG. Then I output is the output of the device, output current of the device. L degenerated is the degenerated inductor connected at the source. Now Zin, if you look from this, Zin is equal to 1 by j omega CGS plus j omega into L degenerated plus LG plus GM by CGS into L degenerated, that is equal to RS. So Zin is equal to, why Zin is equal to RS? Zin is equal to RS for matching. If matching is there, then there will be maximum power transfer. So Zin is equal to RS. Now what is VGS in this? VGS is equal to mean of ENS, or mean of the noise at the source, mean of source noise divided by RS plus Zin. Zin is equal to RS, that we can put later. So RS plus Zin all into 1 by j omega 0 CGS. So that you can put as mean of the source noise divided by 2RS into 1 by j omega 0 CGS. Now 2RS, 1 by 2RS j omega 0 CGS is equal to Q. So now put that, if you put that, then VGS is equal to Q by J into mean of the source noise. Now I output, noise output, IN output is equal to GM into Q by J into the mean of N. What is that? I output is VGS into GM. So VGS is equal to Q by J mean of ENS. So putting that IN output is equal to GM Q by J mean of ENS. So that implies that on the variance of I output or output current, output noise current variance is equal to GM into Q square, and that into the variance of noise, source noise. Now we can find out what is the noise factor. Noise factor, we have seen the definition, and we have derived this expression for noise factor. The first expression, GM into Q square into variance of noise, source noise, plus variance of NDG current by delta F divided by GM into into Q whole square into variance of source. And now simplifying that, this is equal to 1 plus NDG variance, NDG current variance divided by delta all divided by GMQ square into variance of noise. Now output these values there of TNS square. So if you put values of TNS square and variance of NDG current by delta S, then noise factor is 1 plus 4 KT gamma GDO into 1 by 4 into 1 minus 2 absolute ZD plus ZD square into 4Q square plus 1 divided by GMQ square 4 KT into RS. So that is equal to 1 by, this is just rearranging the terms. So this is 1 plus 1 by GM into QRS into gamma ZDU by GM into 1 by 4Q or into 1 minus 2 absolute CID plus ZD square into 4Q square plus 1 into ZD square. So that is equal to, again you can see, RS will cancel out in the numerator and denominator, then 2 omega square into, if on Q, you can put 2 omega square RS into CGS. So that will go to the numerator, then in the numerator and denominator cancel out RS. So in the numerator only, which will be left with CGS. Denominator will be GM, so CGS by GM. And then other factors remain same. So that we can write as 1 plus omega 0 by omega t, because 2 CGS by GM is equal to 1 by omega t, just put that. So 1 plus omega 0 by omega t into gamma into GDO by GM into 1 by 4Q, 1 by 2Q, 2, this 2 by 4, so 2 cancels out, 4 are leaving out 2. So now 1 by 2Q into 1 minus 2 absolute C ZD plus 4Q square plus 1 ZD square. This factor from gamma to ZD square, that is called the noise factor swelling coefficient. Now on noise factor scaling coefficient versus Q, that is dependent on Q. So that versus Q curve, if you draw the curve, noise factor scaling coefficient versus Q, then you can, for a 0.18 micron C must be right. You can see when C is equal to 0, the blue lines will 0, noise factor is around 4. When C is equal to minus J0.5, minus J0.55, noise factor is between 3 and 2.5, around 3.25. So that is the value that we are requesting. Lowest value of noise factor. Lowest noise is obtained for Q is equal to 1.5, around 1.5, between 1.5 to 2 is the lowest value. C is equal to minus 1, it again for the lowest noise factor scaling coefficient, lowest. So from this, what you can conclude is, as C value increases, noise factor scaling coefficient decreases. Similarly, Q also decreases. So for lower Q, you get this value. As Q increases, the noise factor scaling factor increases. These are the two conclusions that come from this topic. Then compare the noise factors. Inductor degenerated in the common source configuration and non-degenerated noise factor. Compare these two. If you compare these two, then you will see by the comparison that the noise factor scaling coefficient in case of inductor degenerated CS, it is half of that of the non-degenerated noise factor scaling coefficient. Only that is the difference. Otherwise, these two expressions are same. So the figures on noise factor scaling coefficient comparison figures also show the same thing. Is portrayed by these two figures. Compare these two figures. One with degeneration, other is without the degeneration. With the degeneration, noise scaling factor is much below that. The without degeneration is half. It almost becomes half. Then what is the achievable noise figure? In a 0.18 micron CMOS, when it is power matched, what is the achievable noise factor? See, of this device, usually it operates at between 1.8 to 2.4 gigahertz. So at 1.8 gigahertz, C is equal to minus J 0.55. W is equal to 1.8 micron, L is equal to 0.18 micron, VGS is equal to 1 volt. Using this in the SPICE simulator, that is a simulator called SPICE, it is available free in the web. Go to Google, you can get SPICE. Now it is available free. So do that. Get the SPICE simulator, any SPICE simulator. This is a SPICE simulator, so use that for the device. Then measured value GM is equal to 871 micro-S, CGS is equal to microsiemens, CGS is 2.9 femtofarad, WT is approximately equal to GM by CGS, so that will be 2 pi into 2 pi at 47.8 gigahertz. W0 by WT is equal to this 1 by 26.6. So looking at the earlier curve that we saw, with Q is approximately 1.4, you will achieve noise factor scaling coefficient of about 3.25. Noise factor is 1 plus 1 by W0 by WT, which is 1 plus 1 by 26.6, which is W0 by WT, that into the noise factor scaling coefficient, which is 3.25, multiply, then that will give you 1.12. Then noise figure is 10 log of 1.12 or 1.13, which is approximately 0.49 dB. That is the noise figure. Now, what are the component values to get minimum noise figure? Why you require component values? Because you are designing the low noise amplifier, so you require the component values. So the component values for minimum noise figure with power matching. What is given is RS is equal to 50 ohm, Q is equal to 1.4, F0 is equal to 1.58 gigahertz, FT is equal to 47.8 gigahertz. CGS will be calculated as Q is equal to 1 by 2 RS into omega 0 into CGS, from which you can find out CGS. CGS is equal to 1 by 2 RS into omega 0 Q. Put the values 1 by 2 RS is equal to 50, omega 0 is equal to 2 pi F0, so 2 pi into 1.8 into 10 to the power 9, then Q is equal to 1 by 4, 1.4. Put these values, CGS is equal to 631 femtofarad. Then L degenerated, this will be calculated as GM by CGS is equal GM by CGS L degenerated is equal to RS. So that gives us L degenerated is equal to RS by omega T, that is equal to 50 by 2 pi into 47.8 into 10 to the power 9. So that is equal to 0.17 nanohenry. Then LG will be calculated by from this equation. Omega 0 is equal to 1 by root over of Lg plus Ld generated into CGS. So from that we get Lg is equal to 1 by omega 0 square into CGS minus Ld generated. So put these values, omega 0, omega 0 is equal to 2 pi into 1.8 into 10 power 9. So that square, then CGS value we have found out 631 femtofarad. So 631 into 10 to the power minus 15. And then minus Ld generated we have found out 0.17 nanohenry, which is 0.17 10 to the power minus 9. So that will give us 12.2 nanohenry. Lg is equal to this. Now, next question is whether you have chosen a proper bias point for the amplifier to operate. That is most important part is this bias point. Whether you have chosen the proper bias point. So chosen bias point is VGS is equal to 1 volt. That is the bias that we have taken for this point. So here you will get for low power, lower FT is required. Power should be linear in this region and lower GDO by GM. For high power, which is on the right hand side, you look at the figure. The dashed line is VGS is equal to 1. Left to dashed line is for low power operation. Right side to the dashed right side to the dashed line is for high power operation. So for high power, you require higher FT, higher linearity, so linearity should be better, and higher GDO by GM. So that you can see here, higher GDO by GM on the left side, lower GDO by GM, higher linearity is on right side, lower linearity is on the left side. Okay. Now we have to find out what are the bias current for the design example. Calculate the current density from the previous plot that we have seen. So VGS is equal to 1 volt. That implies that the current density is equal to 175 microampere per micrometer. Calculate W, or that you can find out from SPICE simulation. If it is in the examination, they will give you the W value. So on W, or at least they will give you this L is equal to 0.18 micrometer. CGS is equal to 2.9 femtofarad we have calculated. For W is equal to 1.8 micrometer. Then W is equal to 631 femtofarad by 2.9 femtofarad into 1.8 micrometer. So that will be equal to approximately equal to 392 micrometer. This could also be computed based on COH value. But forget that, just calculate it in this manner. Then calculate the bias current. I bias is equal to I density into W. W we have calculated, I density we have calculated. Just multiply them. That gives you 69 milliampere current. So this is not a low power. Now you have got into problem. 69 milliampere is lots of power. 10 milliampere is also a very good power, very good amount of power. 69 is much higher. So with that we come to the end of today's discussion on low noise amplifier design. We left with what is to be done when you get high current. So if you get high current, then how to divert that current. So that is something that you have to think. Look at some designs in the book, and you will understand how to do that. So with that, we'll stop for today, and best of luck for your mid-sem examination. Next class we will see or something else. Today we prepared in a hurry. I thought there will be no class. Anyway,